Hello and welcome to my channel. In this video we are going to see under what conditions one half space is contained into another half space. This is associated with a sixth question from chapter 2 of Convex optimization book, and we are going to see what are these conditions. Well, the problem simply says that when does one half space contain another, or when two half spaces are equal. And I just want to remind you what a half space is by reminding you a hyperplane. And we saw that a hyperplane is denoted by this equation right here, and a very simple case is a hyperplane in a 2D plane where we have an equation like this. And you remember that we can show that and characterize that hyperplane by its normal vector, which is this vector. And we also explained that that normal vector also shows which side of the hyperplane contains all the points in the half space. What do I mean by that? So A here is 2, 3. Now we have 2 here and 3 here. So A is going to be here. If I were to draw A, then you can see A is perpendicular to that hyperplane, and in order to show all the points that are contained in this half space, so this is going to be a half space. In order to show all the points, we look at the direction of A and then pick the points that are on the opposite direction. So all the points on the left hand side of this hyperplane are contained into our half space. So that was a very brief introduction about hyperplane and half spaces. Now in next slide we are going to see what happens when we have two half spaces. Well, before introducing you all the complicated formulas for as the conditions for the solution of this problem, I just want to show you pictorially what happens when one half space is not contained into another one. So suppose we have half space H1, and here is half space H1, and according to its A, or the normal point, all the points here are contained into this half space. Now, I have another half space here as H2, and all the points here are in the second half space. You can easily see that there are points which are not in H2, but they are in H1. Therefore, H1 is not contained into H2, and H2 is also is not contained into H1. However, we have another case where we have H1 as the first half space that we introduced. So all the points are going to be here, and all the points inside the third half space would be all the points right here. And now you can see that all the points that we have in H3 is contained in H1 as well. Therefore, we can say that H3 is contained in H1. But what is special about the second case, that one half space is contained into another one, and that point is that if you just were to draw A for one of them, A for this one is going to be this, and A for the other one is going to be the same. So these two are in parallel, and actually in this case these two exactly are equal because we have 3 3 and 2 2 here. And in the next slide, I am going to introduce all the conditions under which we have uh, one half space containing into another one. Okay, what did we learn? We learned that we have a half space H, which has A with no tilde, and half space H tilde, which has A tilde and B tilde. And we are saying that H is contained in H tilde if and only if that statement holds true. So there exists a lambda greater than 0 such that for lambda, normal vector of H tilde half space has to be a multiple of normal vector of the other one, and then B tilde has to be greater than lambda B. Why is this the case, and what is the role of lambda? So suppose we have a half space H. If you multiply by lambda, which is greater than 0, you're not messing up with this inequality, so we preserve that. And if that is the case, so we are going to have lambda times A transpose, which is going to be A tilde transpose, and we have B tilde, therefore we can include H in H tilde. And this is the case, for example, for this one. We have one half space here, and if I multiply by 2, I'm going to get 4x1 plus 6x2 less than 12. And now you can see that B is less than 18. I can claim that the first half space is contained into the second one, and this is the necessity and sufficient condition for the result we are looking for. So in next slide, we are going to explore that further. Okay, we have a two-sided implication. For the first one, we are assuming that if there exists lambda greater than 0 and A tilde equals lambda A and B tilde is greater than lambda B, therefore H is contained in H tilde. In order to show this implication, first we pick an arbitrary point in H, and because that arbitrary point Z is in H, we can just plug Z in here to get this inequality. And once we have this inequality, we can multiply by lambda to get this inequality. And because we know that lambda times A equals A tilde, we can put A tilde transpose here, and this is less than lambda B. Also, we know that lambda B, according to this assumption here, is less than B tilde. That means A tilde transpose is less than B tilde, and that exactly is a point on H tilde. Therefore, we started with a point in H, and then we ended up with H tilde. Therefore H is going to be in H tilde, and that's one side of the implication. And in next slides we will show them for the other way around of the implication. Actually, the other implication is more difficult than the first one, because for this implication, we are assuming that if H is contained in H tilde, then there exists lambda greater than 0, and these two conditions hold. I can simplify that statement as if H is contained in H tilde, then A and B, where A and B are two different conditions that we have. B is this one and A is the first one, saying that lambda greater than 0 and A tilde equals lambda A. So this implication can be shown by picking contradiction methods. So suppose to the contrary, not A and B. Not A and B means that not A or not B. That means negate A and negate B. This is coming from the Morgan law, and I will show you in next slide when we negate A and B what happens. Okay, we want to prove this by contradiction. That means we need to come up with all the conditions and show that if we assume something false, then we are contradicting with the assumptions that we are assuming they're true. So I said that we want to negate A and negate B. Let's see what is A. A is a statement that says there exists lambda greater than 0 such that lambda times A equals A tilde, and then B is B tilde greater than lambda B. Not A means there is no lambda greater than 0 such that A tilde equals lambda A, and that can be broken up to three different cases. First case says that there is a lambda where we have no equality. And the second case is the case that lambda is less than 0 and we have this equality. And the last one says that lambda equals 0 such that A tilde equals 0. We are not going to address this one because if this is the case, then there is no H tilde since A tilde equals 0. And not B means that B tilde less than lambda B. So we are going to have three different cases for which we need to examine if we get a contradiction or not. And notice that for negating A, I didn't assume negating B because it doesn't matter. We just need to have the negation of A or negation of B. And based on those, we are going to define three different cases, which I will explain in next slide. Okay, I said that suppose to the contrary, the implication is not true. That means there is a lambda where we have this not equality, and then lambda is less than 0, and the last case would be the case where we have B tilde is less than these two. So for the next slide, we are going to examine the first case. But what does the first case say? Before showing you the formula, I am going to show you what is going on here. So I have two different hyperplanes here, and these hyperplanes are not parallel. So we have A for this hyperplane here, and then we have A tilde for this hyperplane here. And as you can see here, A and A tilde are two different vectors because they're not in parallel. And what I am going to show you is that if we pick a point here, for example, as x hat, and if I pick a direction perpendicular to this A, and if I go toward that direction, then I'm going to shoot to the point where I get another point that is not in H tilde. and all the points that are here are in H tilde, and if I get a point here, that means I have a point that is not in H tilde, but it is in H. But we want to show this rigorously. In order to show that rigorously, so we say that there exists a vector in Rn such that that vector is perpendicular to A, and that means V transpose A equals 0, and that V has a property saying that V transpose is not perpendicular to A tilde. But why this is the case, and we can prove that. So suppose V is perpendicular to A tilde as well. We know that A tilde not equal lambda A. If we multiply by V tilde, we get V tilde transpose times A tilde equals lambda V transpose A. And because we know that V is perpendicular to A, we get 0, and if V also is perpendicular to A tilde, we get 0, and we get 0 not equal to 0, which is a contradiction. Therefore, the vector V is perpendicular to A, but it is not perpendicular to A tilde. So let's see what we can do with this vector in the next slide. As I explained, we are going to pick a point x hat that is in the intersection of H and H tilde, which is a point right here. This is suppose the normal of H is here and normal of H tilde is here. Therefore, x hat is in the intersection of H and H tilde. And we are going to go toward this direction to get to this point, which is not in H tilde. So what we can do is that we are taking a point in X. We are taking x hat as our point in the intersection of H and H tilde. Because x hat is in H, we have this inequality that holds for x hat. Also, this inequality holds for x hat here. So I can write A transpose times x hat, and I can add 0 to that. Because I know that V is perpendicular to A, I can just place A transpose V in place of 0 to get the second equation, and now I can factor out A transpose to get this point for any t in R. Now, I want to examine what is going on with H tilde. So with H tilde, a point is here and it satisfies that inequality. Now, if I just add that direction which I explained to this to the left side of the equation, then we are going to get two different values. When H tilde times V is less than 0, then I can pick a t less than 0 and then find a t as small as I want to violate this inequality. And when A tilde transpose times V is greater than 0, I can pick a t that is very large and is greater than 0 to violate another inequality. When I violate these two inequality, that means I have a case where a point is in H, but it is not in H tilde. Let's conclude in the next slide. Okay, we saw that by picking this direction and this point, we can violate that inequality. And once we violate that inequality, we have a point that is not in H tilde, but it is in H. And we have this statement which is a contradiction to what we assumed, and we assume that H is contained in H tilde, and that concludes the first case. In next slides, we are going to handle the second case. Second case is a case where lambda is less than 0. That means also we have this equality, and that means both the hyperplanes are parallel. However, their normals are pointing toward the opposite directions, and we want to show that this cannot be the case. Pictorially, what I am going to do is that I will pick a point x hat here, and then I am going to go toward the opposite direction of A to get to a point, let's say here, and that point is not in H tilde, because all the points in H tilde are on the right hand side of the hyperplane that is here. So let's take a point x hat in H. Once we have that, we have this inequality. Now pick a point as this point which is in H for any t greater than 0. Why this is the case? Because once we have that point, just multiply that by that point in order to get A transpose x hat minus t norm square A. And for t greater than 0, we can see that this inequality holds always. So we have this point, and we are sure that this point is in a point in H. Okay, let's see what we can do with this point in next slide. Now let's use that point we defined for H and evaluate that point for the normal of H tilde, and then just multiply it by A tilde. So once we multiply that by A tilde, we get this minus t times A tilde transpose times A. And we know that A tilde is lambda times A, so we have this relation, and we know that lambda is less than 0. We know t is larger than 0, therefore this is together with negative sign is going to be positive. Now if I increase t, I can violate that inequality and have all these greater than b tilde, which means that x hat minus t is not in H tilde, and finally we get H is not included in H tilde, and this is a contradiction to what we have assumed for our assumption. So that concludes the second case. In next slide, we are going to see what happens to the third case. Okay, for the third case, we have that A as our condition, A, which is this one, holds, but B does not hold. And what I'm going to show that is to have two different hyperplanes, H tilde and all the points in H tilde are going to be these points, and all the points in H are going to be points like this. And now you can see H tilde is contained in H, but H is not contained in H tilde once lambda b is greater than b tilde here. The way that we can show this is just to pick a point x hat here on the hyperplane. Because it is on the hyperplane, it is included in the half space H, and we have equality here. Now let's use that point and evaluate it on the H tilde to see what happens. So if we multiply that by A tilde, then we have lambda times A. This is our assumption, and we can pull that lambda out. We have A transpose times X hat. That would be B tilde, and I'm sorry, B lambda times B is here, and we know that lambda times B is greater than B tilde. Therefore A tilde is not less than B. A tilde transpose X hat is not less than B tilde. Therefore X hat is not included in H tilde, and we have this inclusion, which is a contradiction to what we assume. So we went over all these three cases, and now I want to recap in the next slide. Okay, we saw that for all three cases, H is not included in H tilde, and we got contradiction because we knew that this is true, and by assuming the opposite of the implication, we got the opposite result that we assume that it is true. Therefore this cannot be the case, and we just showed that once we have H contained in H tilde, there exists lambda greater than 0, such that A tilde equals lambda times A, and B tilde is greater than lambda B. So that concluded the first part of the problem. Now we are going to address the second part of the problem in next slide. Okay, we want to see under what condition two half spaces are equal. That means these two are equal. So for the set equality, we need to have H uh, included in H tilde and H tilde included in H. And we just proved that in order to have H to be contained in H tilde, we need a lambda that is greater than 0, and to have this equality plus this inequality. Also, for the other one, we need to have gamma greater than 0 such that we have this equality and this inequality. Well, once we have these two, we can come up with a condition that is a necessary and sufficient condition for having two alpha spaces equal. And I'm going to show that in next slide. Okay, so from the first condition, we have this, and we know this holds true. Because lambda is greater than 0, we can write 1 over lambda times A tilde equals to that. And from the second condition, we have this equality. If we just look at this, A is here, and gamma times A tilde is this guy. If I just make lambda be gamma, then I would have these equality for both. And also, if I just change uh, that inequality to this one, I can compare this, and because now I know that gamma equals 1 over lambda, so I can fix these two inequality by saying that just b tilde has to be equal to that, and now we have all the conditions we wanted, and I'll uh, simplify them in next slide. Great. We are on the last slide for this question. I know it got a long video, but I had no choice because I wanted to explain every detail of this question. So the condition under which we have two half spaces equal to each other is the same as the conditions we had, except we have to have the last inequality as equality. And that concludes the solution for the problem. And the takeaway for that problem is that we realize that under what condition a half space is contained into another one or equal to another one. Thank you for watching my videos, and I hope you've enjoyed this video. You can support me by just liking videos and giving them a thumbs up and subscribing to my channel. Also, it will be a huge help to share my videos with anyone who you think would find them useful. Please let me know if you want me to solve a specific questions in the comment section below, and I will create a video for that. Have a very good day.